In the third week, we will talk about the introduction to neural network. Okay? So, introduction to neural network. Okay? So, in the first place, we need to talk about the neurons and the brain. Okay? Which we have this feature. And so we can think about it. So, in physiology, we have this kind of nucleus, just like this one. Okay? This is nucleus. And so, we imitate the feature of this nucleus in order to transmit the currents by using the axon in here, just like this one. And so we have some synapse, okay, just like this one. And so this synapse connecting to another nucleus in physiology, okay. And so we have the axon and also a nucleus in here, just like this one, okay. So also we have an input current into this nucleus. For example, I. This is the current, okay. And so at every nucleus we have a threshold, okay. And so if we have too much current on the nucleus, and then we can trigger this nucleus in order to transmit another electrical current to this axon, okay. And so after that, this axon is a main cable in order to transmit our current in here. And so we can split this current into the parts. For example, 1 ampere, okay, and then 2 and 3 and 1.5, okay. And also we can transmit this current using the 3A, 3.5A, and we have 1A, and we have also 0.5A, okay. But what's the difference between these currents? We have some special connection in here, which we call it the synapse, okay. And so this creates or conductance between neurons. Either we can stronger to this current, or we can weaken to this current based on this connection, okay. We have an empty space in here, which call it the synapse, and so this space is too close to each synapses, and so the current is transmitted fully. But in the other case, we cannot collect or transmit the whole currents. For example, 2 ampere, which is going in here, it's transmitted to 1 ampere. And so we have this connection in here, just like this one, and so this is weakened. This is weakened. But in this case, we can strong in here, just like this one, okay. And so in summary, if we have applied the current on the nucleus, and so we can store the energy or the voltage values in here. And so if this voltage is close to the watt or exceed the threshold values of this nucleus, and so the main current is triggered in here, just like this one. And so if this is the case, and then we can create or collect or transmit all the currents into another neuron, okay. In the previous lesson, we have talked about the perceptron structure, okay. And so in order to understand this, or in order to use this concept in the maths, we can build our basic mathematical notation or standard definition based on this physiological property. We can imitate it, okay. And so we can draw the nucleus in here, just like this one, and so at each current in the math is considered as the feature. And so maybe it's the X3, and so this is the feature 1, this is the feature 2, and this is the feature 3. Okay, and so we have an output current in here, just like this one, like the axon. Okay, and so if we have the nucleus or the threshold values in here, and so we can assign the activation function to trigger this neuron with the help of the X0 bias value. Okay, this bias is considered as the threshold in the math. Okay, and so this Y is the output can be generated with the with the HX. Just remember the previous lesson we have talked about the model and training class and the training group. Okay, and so if you want to design this concept or the perceptron based on this information, and so at the when the voltage stored in neuron, which is called the activation function, and so exceed the threshold, which we call it the bias value or the X0 value, and so the current is triggered, just like in the physiology, as Y. Okay. This is the perceptron definition in the mathematical notation. Okay, if we have any input value just like this current, and so we can call it the X1, X2 and X3, and also we have a threshold value, this is the X0, and so if we apply to anything into the activation function, we can generate the some outputs in terms of the in terms of the Y value in here. Okay. So what's the result of this conclusion? In the math or mathematics, we can create the map between the input, this is the current, and the output, this is called the output triggered current. Okay, and so we can generate a new current based on based on applying some input values to the nucleus. Okay, and so this nucleus creates the this form of output. Y is equal to the H. Instead of using the scalar value, we can use the X is a vector or the matrix in here. Okay. But this is the one case. This is the standard perceptron. What about the brain? In the brain, we have 1 trillion neurons, right? Or we have a lot of neurons connected to each other, like this one. For example, if we have the 3 nucleus or the activation function in here, which we call it the neuron in here, and so we can assign to the X1 or we can assign to the X2. Okay, and so for example, this is the eyes, input, what's this the image, or the other one is the nose. Okay, this is the smell. And so if the brain collects the whole information, we have the 3 neurons, N1, N2 and N3. Okay, and so this X1 is connected or linked to these 3 neurons, just like this one. Okay, and so with the with the synapses. And so how we can model this synapse value in the in the math? We can use the brain neural network or the what model parameters in here. And also we can generate the what in the output of these terms, just like this one, Z1, and also Z2, and also Z3. Okay, and so this is the what, these three terms are the outputs of the N1, N2, and N3. Okay, and also this possess to what its own synapses, just like this one, I1, I2, and I3, and I4, I5, I5, I6, and also we have I7, I8, I9. Okay, and then how we can collect or the process this information or these currents based on this information. And so we have also another synapses in here, just like this one, and also this synapses going to the what, to the new neuron. Maybe this is the decision neuron. It decides to what, to act or move to the person or the arm. We don't know, but we can generate another output in here from the what, M4, and so this is the Z4, and maybe it goes to the what, for example, to the muscle. Okay, or for example heart, or for example we can talk based on these currents in here. We don't know, but the total process is collected with the what, with these terms, and so this is also a synapse. Okay, this is empty space, and so just like this one, and so this is modeled, this empty space as a synapse. Okay, and so in order to build the threshold value, each neuron has on its bias value x01, x02, and x03, and also this has the x1, 1. Okay, because this is the second layer, this is the first layer which we call it the 0, this is the second layer which we call it to the what, to the 1. Okay, and so we can model the synapses as a weight or the theta value in terms of what the previous lesson model. Okay, and also we can create another variables in here in order to what, in order to model the second synapse connections. Okay, and so how we can do that? This is the physiological analogy on the what, on the brain, in a simple way. But in order to understand this, or in order to model this, each neuron has specific activation depending on the what threshold, which is called the X0, and synapse connection, which we call the theta in this case. And so the output of each neuron is to what, Zi is equals to the what, 1 divided by 1 plus exponential term minus theta transpose times x vector. Okay, and we can use as an activation function as a sigmoid or tan h or linear, but just remember that this activation function must obey the property of the hard nonlinearity. What is the meaning of the hard nonlinearity? Just remember the digital signal processing lesson, guys. If we are using the sigmoid function just like this one, we have this kind of output between 0 and 1. Okay, and so each value are separate or the distinct value for the what, for this x-axis or theta t times x matrices. Okay, this is called the hard nonlinearity. We don't have any frequency component on this activation function, otherwise we cannot learn this representation between the input and output. Okay. And so how we can model this property in the math as an analog model. In analogy, we can draw the whole picture, like in this one. We have the input value x1 and x2, okay, and so this is the input neuron, and also we have the another neuron, and also we have the one other neuron in here, just like this one, and so the total output is the y, okay. And also if we have the x1, this is the input neurons, we connect the whole neurons into the what, into the second layer, because we have a synapse in here, just like this one. And also we can connect the second layer into the what, into the third one, or the output layer, okay. And so at each case, this is the synapse coming from the physiology, and so this is also a synapse, okay. And so what's the parameter of these things? This is the theta 1 1, this is the 1 2, this is the theta 1 3, which means that this is the first neuron, it's going to do what is the third one, 1 3. And also the other parameter is the what, this is the theta 2 1, this is the theta 3 3 2 2, and this is the 2 3, okay. It's coming from the what, the second neuron is going to the what, to the third one, okay. And also we have a synapse value in here between the what, the axon and the nucleus, and so we can write it just like this one, w1 w2 and w3, okay. And so each of the neuron can be considered as a perceptor, but in a total form, this is called, we have the multi-layer in here, just like this one. This is the multi-layer perceptor, or this is called the neural network. This is the graphical definition of the what, the neural network. And also we should say that this is the input layer, this is the output layer, and also this is the hidden layer, which we call it, okay. So any question? Okay, if you don't have any question, and so we will continue with the what, with the looking deep inside to the perceptual mechanism in terms of the mathematical representation, okay. And so if we have a perceptron, in Turkish algılayıcı, like we have this representation, and so we can draw the what to the function of dot in here, and so this is the plus 1 w0, this is the bias term in here, and also we can fit the what, the x1 value, x2 value, and blah 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 up to what, xd. D is the number of the inputs, okay. And so these terms x and plus 1, this is the bias value, are fed into the what, into the function of f, and so we can generate what, the y value. In the mathematical representation, we can just write this one, the y is equal to the what, this one, j, starting from the 1 up to what, up to d, because we have the number of d at the what, at the input neurons, and so we can multiply wj times xj plus w0 times 1, okay. And so this is called the total input. This is the threshold. And also we utilize in this case, the what is the linear norm, because it collects the whole term, summation with the whole term, just like this one, and so W1, W2, and WD, and so we can generate to the what to the output of the sequence. Okay. So, but what's the meaning of the geometrical representation of this neuron? In the first place, assume that we have only two features. In geometry, we can draw the what to these two axes in here, just like this one, x1 and x2, and also we can draw the what the right angle in here. Okay, and so this x1, maybe this is the mass, maybe this is the length. Okay, we don't know, but if we have two inputs, and so these two inputs are distinct or separate part of the feature. If we have two input values, and so we have two axes with the right angle. Okay, and so what's the meaning of this y value in here? And if we draw these things, and so this is called the hyperplane, guys. What's the meaning of the hyperplane? If we have this feature, and so we can draw to the what to the one axis in here. We can draw to the what to this one. Okay, and so this is hyperplane. And so what's the formation of these terms? This hyperplane is a line in terms of the what, the 1 times W0 plus x1 times W1 plus W2 times x2, which is equal to the 2. Okay, where is coming from? This is coming from to this one. This is the y. Okay, and so if this is the case, if we change the W1 or W2, and so we can change the orientation of this hyperplane in here. Okay, but how we can divide or assign these two space in here? We divide the whole content of the x1 and x1 and x2 space in here, and so maybe we must assign to the what to this place as a 1, to this place as a 0, as a classification problems in here. And so how we can do that? This is the output of the y, and so if you are using the activation function, just like in the nucleus, and so we can assign to the what 1 plus exponential term minus wt times x vector in here, and so we can coding or generating another axis in here, which is right angle to this one. This is called to z. Okay, and also this is perpendicular to the what x1 and x2. Okay, this is a separate feature. And after that, what about this one? In this case, we should assign the 0, we should assign the 1, and so this shape is going to the what to this one. And so after that, we have a region in here, and so this is the 1 and this is the 0, which is coming from the what, this z formulation. Okay, and so this should be converted into the what, into the y, and also we have an activation function in here, and so we can generate the z. Okay, this f only collects the what to this term, which is creating the what to the hyperplane. And so this hyperplane is used to what to separate to the what the whole space into the two parts. And so we want to assign the one part as a 1, the other part as a 0. Okay, and so if we are using the perceptron, we can create another axis, another dimension to what to decide what is the data, which is classified as a 1 or 0. Okay, and so in the perceptron, which we can call it to the what simple hyperplane, guys. Okay, nothing more. The perceptron which is given with this formulation, and so which is called the hyperplane. And so hyperplane is utilized to the what? To divide the whole space into the two parts, 0 and 1. And so how we can assign or evaluate these spaces, and so we can apply the sigmoid function. It's giving to the what in the one space, which is equal to 0, in the another one, or the upper of the hyperplane, which is equal to the 1. Okay? And so, in this case, we can divide space into parts and condition with activation function, guys. See? The perceptron is utilized for these purposes, nothing more. Okay? Any question? Any question? Okay. If there's no question, and so we will continue with the next question. First of all, now we can condition or assign to the what data into one of them spaces, which means that we can classify it or can fit the classification or fitting problem, the hyperplane, to state. This is a general conclusion of these terms, okay? And so, if you are using the perceptron, either we can classify data or we can fit or regress to any data set for a given what input. And so, we can conclude also this one. Perception is directly related to the what? The hyperplane creation, guys. Okay? Nothing more. And so, if we collect or if we are using the neuron, this neuron collects or divide the whole space into the two parts. Okay? And so, after this knowledge, what if there are more hyperplanes? For example, select the two features. With the hyperplanes, just like this one. For example, if we have the x1 and x2, x1, x2, okay, and so also this is the what? The hyperplane 1, or this is what? The hyperplane 2, h1 and h2. For example, this h1 is collected with what? The v0 times 1, w1 x1 plus w2 x2. This h2 is equals to what? Theta 0. For example, this is the another coefficient in here, times 1, theta 1 x1, theta 2 x2. Okay? But just see that we have two hyperplane in here with the different orientations. And so, how we can divide the whole space in this case? What the number of the what? The space. It's different from each other. We have, for example, 0 and 0 space in here, or 1 and 0 space, or 1, 1 space, and so 0, 1 space. And so we can code to the what? To the 4 space with a different output number in here, just like this one. And so we can say that we have 4 different new regions in here that we can classify guys. Okay, and so if we add another more hyperplane, and so we can build to the what 8 plane, which means that if we have 2 hyperplane, 2 over 2. If we have 3 hyperplane or 3 neurons, we can collect or classify 2 over 3, which is equals to 8 region in here. Okay, but in structure, it looks like or we have what x0, this is the bias value, which is equal to the 1, okay, and also x1 and also x2, okay, and so we have 2 hyperplane, which means that we have 2 neurons in here with these nominations, okay, and so this is the 1 neuron, this is the another neuron, okay, and so this is the 1, and this is 1, this is 2, and also we can connect this terms in here. This is the function of h1, this is the function of h2, which is the defines the hyperplane, and after that the sigmoid function is applied in here, just like this one, and also we can generate what the 1 and 0 output in here, okay, and so this is just like the binary coding, right? And we can say that the sigma is equal to what 1 plus exponential term for the what, for example, the coefficients is written in the A matrix in here minus A transpose X vector, okay, so this is the physical representation of the what of this geometrical shape in here, or we can draw this shape in here, x1, x2, and also we have 2 lines, this is the h1, this is the h2, and so this is the hyperplane, and so we can code the what of all the terms 1 1 0 0, and also 1 0 1 0, okay. This is just like this one. We have the difference in here. Okay, guys. This is the 1 and 1, the 0 and 0, and so 0 0 1 1. Okay. We have 4 regions in here. So, in conclusion, we have built the what the R neurons with multiple times, okay, and so each neuron at the same layer creates to what to hyperplane, divides to the what the whole region into the 2 parts. If we are using the 3 neurons at the same level, and so we can divide this whole space into the what 2 over 3, which is equal to 8 different regions, okay. This is the basic utilization of the geometrical representation, meaning of the what of perceptron structure. Any question? If there is no question, so we will continue with the multi-layer perceptron. Multi-layer perceptron. Okay. For the multi-layer perceptron, first of all, suppose that there are some data distributed on the plane like this one. For example, again we have the 2 x1 and x2 features in here, and also we know that this x is on the same class, this O on the same class, okay. For example, if we are using this term, this is called the C1 and also this is called the C2. Okay, we know it. This is a prior knowledge. Okay, and so we can conclude that now C1 and C2 are intersect. And we don't wanna do this. First of all, if we have these informations, and so suppose that if we are using only one hyperplane, for example, x, or if we are using only one hyperplane, for example, if we draw this is the 1, this is the 0, but this 0 region contains x and o value, which is incorrect. Okay, this is the 1, this is the also incorrect. Okay, and so also we should divide these terms in here with the two hyperplanes in here, just like this. But we don't want to do this in here, because if we have this information, we cannot separate this C1 and C2 with the one hyperplane in here, or we can define another model in here. For example, select the G function in here, just like this one. For example, x1 minus theta 2 divided by theta 1 square plus x2 theta 4 square divided by theta 3. Okay, and after that h is processed with what? With the sigmoid function, exponential term g dot. This creates the what? The ellipse, right? And so this ellipse can be built containing to the what? The C1 values in here with the proper initialization or the training phase of the what? The theta values in here. But this is a non-linear. We cannot model. But if you are using this proposed function, this is a model function, and so we can model this C1 as a non-linear. But we don't want to do this. We just only utilize the hyperplane in here. And we can conclude that, however, we cannot do it. Any function to any model, because this is a specific purpose function. Maybe this O value is going to do what? To do this one, and so this ellipse cannot be applied on this data. Okay, so it's too difficult. And maybe impossible for every case. Okay, but this is called the kernel based neural network. Okay, it's a nonlinear hyperplane function in order to what? In order to design your hyperplanes in the what? In the ellipse or the square form or the circular form. Okay, it's another topic of the neural network, but we don't want to do this. Okay, so how we can solve this problem? The solution is simple, just like this one. Use two perceptron, like in the previous case, right? We have the x1 and x2, and so this is the x, o, and so we can build the what? The one hyperplane, another hyperplane in here, and so this is called the 1, it's called the 0 after the processing of the iteration function, and so this is 1 and this is the 0. Okay, and so this is the region of the what? The 1 and 1, and so this is the region of the what? The 0, 1. Okay, and so this is the region of the 0, 0, and so we have 3 regions in here to classify it. And we can classify data in here, but how? So if this is the case, we need to evaluate these regions 1 1, 0 1 and 0 0 by adding with the what? With another neuron into the what? Another layer, which is called the output layer. Okay? So in this case, if we have this information, and so we can collect all the terms as a summary, just like this one. Therefore, we have these formations. We have two inputs, x1 and x2, right? And so we have two neurons in here, just like this one, F and F, right? And so we can connect all the inputs in here. This is the W11, this is the W12, this is the Q1, this is the W22, okay? And so also this generates the Z1, and this is the Z2, which is called to the what? R regions. And also we have the G functions in here, and so output Y can be built based on this information. And so what is the graphical representation of this term? We have two terms in here, okay? And so this first term, Z1 and Z2, is generated in here, which is called to the what? We have two axes in here, X1 and X2. This is the input, right? And so this is the right hand, okay? X, X, O, O, okay? And so this is called to the what? Z1. This is called to the Z2 hyperplane, okay? And so this is the 1, 0, 1 and 0, right? And so F1 and F2 is applied on these terms, and so generates to the what? To the output of the Z1 and Z2. And so what about the second term? In this case, what's the output of this G neuron? This G neuron is built with the what? With another dimensions, which is called the Z1 and Z2, right? And so in the first place, if we have the 1 in here, and so this is the 0 and 0 point, and this is the 1, okay? So this X and X values is going to in here, this O and O value is going to in here, okay? And also we can draw this hyperplane. This is the what? This is the G hyperplane. And so this term is called 1, is called and 0, right? Because we code it. Just see that X is going to the what? To 1. And also Z2 is 1, right? And so Z1 is equals to the what? Is equals to the 0. And also Z2 is equals to the 1, okay? And so Z2 1 value contains the what? The O value. Z2 1. But Z1 must be equals to the 0, okay? And so in this coding, this 2O value is around to the what? Or at the point of the Z2 is equals to the 1, Z1 is equals to the 0, okay? Because in this region, you see that 0 and 1. In this region, 1 and 1. In this region, 0 and 0, right? See? In this case, if we have these informations, and so how we can analyze or build these informations? This X is removed in here, just like this one. This is not true, right? And so the Z2 possesses the X and Z1 0, okay? And so one X is going to be in here, and another X is going to be in here. But in this case, we can draw the hyperplane just like this one. And so this hyperplane generates the what? To the Y. This is equal to the 1, and this is equal to the 0, okay? And so this is the one layer. This is the another layer, which we call it in the if we collect the whole terms, we can say that this is called the multi-layer perceptron. Okay? And another calling this mechanism is called the neural network. If this is going to the forward, and so this is called the feed forward neural. Okay? But if you are using the what the x1 and x2, this creates the what the axes or the space. And so if you apply any function in here, just like this one, and so this creates the hyperplane. And so we can generate the R output 1 and 0, z1, z2. And so this z1 and z2 creates the another space in here. Just like this one. This is the second space, second layer. And so z2 and z1 are considered right now as an axis. And so how we can collect the whole terms? If we are using the activation function, we can generate the whole these terms into the what? Into the two parts. We collect the 4 parts, divide the 4 parts at every region. In the second place, we divide it into 2 parts, which means that we can classify all the terms based on this information. This is the simple what XOR solution based on the neural network or the multi-layer perceptron structure. Okay? Any question? If there's no question, then so if we have this structure, then we have x1 and x2, and so we have two neurons, a1 and a2, b1, b2, and also c1, c2, and also we have the output value in here. If we have two neurons, and so we have two connections at each layer, okay? And so what is the geometrical representation of these terms? First of all, what is the input of the first layer? This is the x2 and x1, right? And so what is this term? This is the a2 and a1. And what is this geometrical representation? c2 and c1. And so after that, the output of y can be generated 1 or 0 in here. Okay? And so if we have more than one layer in the what? In this place, this is the output layer, this is the input layer. But if this space more than one layer, which we call it the deep learning or deep neural network, nothing more, because we have too many hidden variables in here, a1, b1, c1, and so we cannot show these values in the graphical representations. And so this is the basic definition of the what? The deep neural network. And so in order to train this network structure, we need to use the deep learning. Okay? Nothing more. That's it. So, any question? If you don't have any question, and so we need to continue with the derivation of the structure of the neural network in the general representation. Okay? So first of all, so we need to define the output layer in here, just like this one, y1, and also yi, this is the index, and so we have the yk, but this is the big, okay? I is going to do what? Up to the k, okay? And also we need to define the hidden layer neurons in here. Okay, this is going to do what? The I in this, just like this one. This is the general representation, and the coefficients of these terms is equals to the what? V I H. Okay, and so this is the Z0 plus 1, because this is the bias term in here. This is the ZH. Okay, this is the general, and so this is the last hidden layer neuron, Z bigger H, and so this H is going to do what? Up to bigger H. And also we can define the 3 neuron in here with the parameter x0 is equal to plus 1, and so xj and up to what? Xd. Okay, and so this j is going to do what? This is the index, this is the biggest number of these neurons. Okay, and also we can write these terms. Okay, and every coefficient is equal to what? W H J indices in here. Okay, so how can we calculate to the what? To the output value for a given input? And also this is the hidden. Okay, hidden layer. And so ZH is equals to the what? Is equals to the 1 divided by 1 plus exponential terms minus summation operator Z is equal to the 1 up to VH J times X J plus WH0. Okay, this is the base. Okay, for sigmoid function. Just remember that. Okay, and after that, what about the yi value here? Vi transpose times z, which is equal to the what? H is equal to the 1 up to h, and VIH times ZH plus Z is 0. Okay, and so these two functions are used to do what? To generate the output for a given input value in terms of, or the after processing with what? The W and V matrices or the neural network coefficients. Okay, and so in general term, XT is mapped with the YT. Okay, this is the map. Okay, but the main problem is that how can we train the network? Just remember the previous lesson. In the previous lesson, we utilized to the what? To the variables. In order to what? In order to update the R model parameters. Theta 0, theta 1. For the what? For the linear regression, multi-layer regression, multiple regression, or the classification problem. Okay? And so, in the general term, which we call it to the what? To the back propagation algorithm. The Nobel Prize has been won by the derivation of this algorithm by the Roman heart. Okay, so first of all, just remember the previous lesson. In the previous lesson, we first of all defined the cost function, right? We built the cost function like this one: E, W, and V for a given x is equals to what? 1 divided by 2 summation operator T. RT is the what? Is the training data or the target data, and YT score. Okay, this is the positive definite cost function with RT is the target values. Okay, and so after that, select the activation functions. Just remember the previous lesson, we select what? The sigmoid function or the linear function. But in this case, in order to build the hard nonlinearity in here, in the first place, the input is assigned with what? The linear neuron. Okay, and so hidden layer is called or selected with the sigmoid neuron, and output is assigned with the linear neuron. But we can select everything in the what? In the sigmoid. What is the linear neuron? Linear neuron means that x1 times 1. This is the linear. x2 is equals to x2 times 1. Okay? So what is the sigmoid 1? Sigmoid is equals to what? 1 divided by 1 plus exponential term minus theta transpose x vector. And also in the output, the y is equals to v transpose times z value. Okay? This is the R structure. And so we need to derive the R update rules in here. Just remember the previous lesson. In the previous lesson, update rule is a simple for the backpropagation or gradient descent. V is updated with what? Alpha times d total cost function v. This is the output to hidden update. And so W is updated W minus alpha dE to W, right? And so alpha is the learning period. Just remember the previous lesson, okay? And so for hidden to output layers, we have dE partial derivative for a given x dE is equals to what? The cost function is equals to the summation operator of these terms RT minus, this is the output neuron, YT is equals to what? The total number of hidden neurons in here, VH times ZHT plus V0 and square and partial operator VH, and so this is equal to 2 times 1 divided by 2. This is the integration operator because we take the derivative terms with respect to the VH, and so the total summation operator RT minus YT times minus ZHT. Okay? This is the first rule. To what? To build the R algorithm or train the networks. Okay? And in second place, this is the last one. For input to hidden. First of all, dE must be applied to the chain rule. dE, dyi, dyi, dzh times dzh, dw. This is the chain rule. It's coming from the calculus of the variation. Okay? In the first place, dyi is taking the derivative of the what? The total summation operator of the what? This is the t and RT minus YT square, and so which is equal to the what? The RT minus YT times minus 1. This is the first part. In the second part, dzh is equal to what? zh plus v0. This is equal to what? The vh. Okay? This is simple. And so dw 1 divided by, because this is zh, and so 1 plus exponential term minus wt x vector in here, just like this one, and so this coming from the zh and zh minus 1 zh. This is sigmoid derivation rule and xj. Okay, and so in the final case we have these coefficients just like this one, t RT minus YT, this is the first term, but minus 1 times VH, this is the second term, and this is the third term. Okay? ZH times 1 minus ZH times XJ T. Okay? So if we have these two gradients, and so we can apply to this rule at each iteration of the neural network, and so we can train our neural networks. Okay?